All right. So we talked about the bipolar junction transistors in the past lecture or so, and we learned about this new nonlinear device. We like it because it gives us control over what is going on in the circuit. We saw that there were two types. There is an NPN transistor and a similar but a slightly let's say complementary device that is a PNP device, PNP or NPN transistors. And we said for these devices we always stick to the convention for the directions of currents and voltages, mostly currents actually in this case. Each device has 3 pins, base, which we normally use to send the command that we have to the device. Collector is the output of the device in most situations, not always. And emitter is where you basically have everything, in most cases, everything measured with respect to that signal. So the base signal is measured with respect to the emitter, and the collector signal is measured with respect to the emitter. And when I say that, it's maybe in 70% of the cases, but there is a good number of cases, good portion of situations where you actually use the emitter to send a signal. And we'll see that we almost never use base as the output for the transistor. Now for an NPN device, this is how we chose the directions of the currents, and we are going to stick to these directions. For PNP, they are the opposite. And we said that we all know that deep inside this device there are 2 little diodes that are connected like this. They are made very, very closely to each other, and that's why we get all those interesting properties for the transistor. And in a PNP device, the 2 diodes are oriented in an opposite way. And then what we said after that was that there are 3 operating regions. There is active region, cutoff, and saturation. And these 3 operating regions depend on what the state of the 3 diodes, the 2 diodes that we just mentioned are. So let's say if you look at the base collector diode and the base emitter diode, in active region the base collector diode is off. Off means reverse biased in this case. It doesn't mean that it is not conducting current, right? So off means reverse biased. Base emitter is on. In cutoff both diodes are off. And in saturation both diodes are on. And we said there's another region, reverse active, that we never use. The region that we usually bias the transistor in and keep it there in analog circuit design is active region. The cutoff and saturation regions are used from time to time for switching purposes in analog circuits. But in digital circuits, we almost always use cutoff and saturation regions for the transistors. So those are zeros and ones. Those are the logic levels that you see in digital circuits. So that was that, and then we saw that there are a couple of foundational equations that you use to solve BJT circuits. The first one came from KCL. Very obvious that the sum of collector and base currents is going to be give you the emitter current. Then we saw that from the device physics, if the device is in active region, the base current is beta times IB or alpha times IE, where if you use the equation in the above, we can show that alpha is beta over beta plus 1. And beta is a number that ranges from somewhere around, let's say, 20 to maybe about 1,000, depending on how you make your transistor. For a big, fat power transistor, this is going to be somewhere between, let's say, 20 and 50 beta. But for a small signal transistor, it is typically in the range of 2 to 300. There are transistors known as super beta transistors where beta can be much higher, close to maybe 1,000, but they are uncommon. They're mostly used in IC technologies. So let's say beta for most typical applications ranges in between 50 to maybe 300 in terms of value. And then for that reason, you can always see that alpha is less than 1, but very close to 1, right? So it's 0.9, 0.99, 0.995, something like that, right? But it's always less than 1, obviously. And then the other relationship we had was between the collector current and the base emitter voltage, which was similar to a diode relationship. We see that, when we had the discussion about the physics of this device briefly, we mentioned that when you turn on the base emitter diode, you inject a lot of carriers from emitter into the base region. So that's your forward bias diode. The reverse bias diode of base collector, if you make it really close to that first diode, the base emitter diode, will gather all of those carriers and put them in the collector region. So your collector terminal in the active region behaves as a one end of a current source because it's a reverse bias diode, and that current is given by the base emitter voltage because it was the base emitter current that was collected and put out at the collector terminal, right? So these are the three foundational equations that we have. And then we also saw that for a BJT, I'm going to draw the model for NPN. We saw at the end of that discussion that NPN and PNP are very, very similar. So if you learn one, you should be able to expand your information to the other one very easily. We use a hybrid pi model for the analysis of circuits with BJTs in them. And if you have a BJT in a circuit, you use this equivalent model to analyze the circuit. So initially you need to solve a few circuits with this model, but over time you can basically see the circuit here and do, or the symbol of the transistor on the left, and do the analysis on that diagram. So for this equivalent model, this controlled current source that you have between the collector and emitter, its value is beta IB or IS e to the VBE over VT minus 1, but we saw that this minus 1 when the device is on is very small compared to VBE over VT. All right, so with all that said, we went and solved BJT circuits and we saw how we can find let's say the voltages and currents in a circuit that has a BJT device in it. It was all DC analysis. And in analog circuits, we said that you have two diodes, like the diode circuits that we analyzed in the past. You have to assume an operating region for the diodes and then go and verify your assumption. Same thing here. You assume the transistor is in one of those three operating regions, and then at the end of the story, once you do the calculations, you need to verify the assumption. Now, the issue is that, how do we know there are actually four possible operating regions, but for analog circuit analysis, especially in practice, normally an active region of operation is a good starting point. That's where we keep most of the transistors in analog circuits. But that, at the end of the story, needs to be verified. Now, what tells us something is wrong? Well, you go and solve your diodes, your transistor circuit, and all of a sudden you see a DC voltage at a node that is beyond the power supply rails. So if your circuit is, let's say, biased with a plus and minus 5 volt power supply, you all of a sudden notice that the voltage is, let's say, 7 volts or minus 7 volts. Or you see that the direction of the current into one of these terminals is the opposite of what you assumed. Or for terms of saturation, you see that the collector voltage for an NPN device is less than the emitter voltage, or vice versa. For a PNP device, you see that the emitter voltage is less than the collector voltage. And those things are basically alarms, flags that will tell you that something has gone wrong. And you go back and maybe check the calculations or assume a different operating region based on what you have seen. So that was the BJT circuit analysis. In this lecture, I'm going to talk about a new type of a transistor, another type of a transistor, which actually dominates the industry right now. So in terms of the number of devices made, 99.999999% of the transistors that are made today are MOSFETs, metal oxide semiconductor field effect transistors. We'll see why we have those many words in the acronym. And BJTs are a tiny, tiny fraction of those transistors. And then you might ask, if there is so few of them made, why do we care? Why do we have to learn about such a small fraction of the transistors? The answer is that, in most cases, you're designing discrete circuits. If you design an integrated circuit, yes, you most likely have to just go and do the design using MOSFETs. But if you are designing a discrete circuit that you want to make on a PCB, you want to put it on a board, you want to try that at home, there is a very good possibility that it's a BJT. BJT transistors dominate the discrete device market by far, right? So if you want to go and find a small signal MOSFET, your options are actually very, very limited. But for BJTs, you have tons of different varieties that you can choose from. So in practice, a lot of you guys will later on go and design circuits on boards. And then you may not design an IC. And therefore, you need to know about BJTs most likely better than the MOSFETs. But MOSFETs, on the other hand, are used more and more in a lot of new applications, like in power electronics. There are certain advantages to using MOSFETs, power MOSFETs instead of power BJTs. And we have to learn about them as well, even though we may not design an integrated circuit. So how does a MOSFET look like, and why do we have such a long name for it? So here is a structure for a MOSFET. What you have is a, let me see, a substrate. In this case, it's a P-type substrate. So this is what you have at the bottom. Okay, and you make everything on this substrate. You take a piece of wafer, silicon wafer, and you make everything on it. Then what we have done here is that you've created two regions that are highly doped with the opposite doping of the substrate. Again, like BJTs, you're going to see that we will have two different types of MOSFETs, N MOSFET and P MOSFET. I'm talking about N MOSFETs here. P MOSFETs will be very similar, basically the complementary device to N MOSFETs. So I've taken this P substrate. I doped two regions that are not very far from each other with the opposite dopant. So in this case, N+. N+ means very highly doped, so the resistivity of that region is small. And right away, if you remember from the earlier discussions, you're going to have a little diode here between the substrate and this region. And same thing here, right? And this diode is off. You don't really have any current through it. Then the next thing I do is that I put the dielectric here. This is the blue section. And then on top of that dielectric, I put a conductor. So a layer of polysilicon or metal. And again, if you go back and check your physics, you immediately realize that this is a capacitor. This combination, a conductor at the top, a dielectric here, and a conductor at the bottom, that's a capacitor. This is how we actually make capacitors on chip, on wafers. So I make a capacitor like that, but what is special about this capacitor is that I have put two highly doped regions at the two ends of this capacitor. The top view will look like this, right? So the top view, I have my substrate. I'm looking at it from the top. Two doped regions at the two ends of this, let's say, capacitor, right? But the gate in this device is not connected to drain and source. The gate is on top of a dielectric. Now, so this is the structure. It's actually, in terms of how it looks like and how you can make it, it is simpler than a BJT. BJT requires very careful handling of the doping levels and switching from one to the other and making sure that the base is very narrow. A MOSFET, you just create two highly doped regions that are not too far from each other, and a metal oxide semiconductor capacitor. So that's the first part of the word. So you have a metal at the top, oxide, this is your insulator, and semiconductor. So this is metal, oxide, semiconductor, right? So that's the MOS part. And this is the structure of a MOSFET. So now let's see what is behind the FET part, the field effect transistor part. With this device, if I go and connect a voltage source, let me move this. So So if I connect a voltage source to here, between source and drain, so let's just call it VGS, or VDS, sorry. It's a very, very small voltage source. So what is small? Let's say 10 millivolts, 20 millivolts, something really small. And if I connect this voltage source between the drain and source of this device and try to measure current, I do not measure a noticeable current. Why? Because, look at these two little guys, these little diodes. They are back to back, right? And you cannot have a current through that diode. Well, you have two diodes at the two ends of this, but in between, from here to here, you have a resistor. But because the diodes are back to back, you don't get a current through this structure. So for small VDS, if I do not do anything fancy with the gate, I really don't measure anything here. Now, what I do is that I go and put another voltage source between gate and source. So this is VGS, okay? And I can play with that voltage source as well. Now, what happens is that, again, for small values of VGS, I do not measure any current between the drain and source part, right? Everything stays the same. Now, let's assume that I put a little bit of positive voltage on the gate. The drain source voltage is still very, very small. Let's say I keep it at plus and minus, plus 10 millivolts here. Very, very small, okay? But I start playing with the gate voltage. And then I put, let's say, half a volt, and then another half a volt on it, and so on and so forth. The substrate I have is P-type. So in a P-type substrate, remember that I have a bunch of holes as my charge carriers, right? In an N-type device, N-type substrate, we had electrons as charge carriers. In a P-type substrate, we have extra holes. So I have my PN diodes and nothing happens. But when I put a positive voltage on the gate, well, it's a positive voltage. It's going to repel the holes. That voltage is going to start affecting the holes through the electric field that is produced. And you will repel the holes away from that region. The other way of thinking about it is that you can bring electrons to the surface. So you obviously have electrons in both P and N-type semiconductors. But in a P-type semiconductor, you have way more holes than electrons. In an N-type semiconductor, you have way more electrons than holes. But you definitely have electrons here and there in both cases. And you bring these electrons closer to the surface, right? So you start accumulating some of these electrons close to the surface. The positive voltage attracts those electrons to underneath the gate. But the insulator stops the electrons from going into the gate, actually. So they just come and accumulate right underneath the gate region. And then you keep increasing that voltage, the VGS. So you put a little bit more VGS on there, positive VGS. You bring in more electrons to the surface. At some point, what happens is that you will have an inversion. So you basically will have so many electrons right here underneath the gate that it is as if you have an N region. Remember, N region means you have more electrons than holes. So you repel the holes and you bring in so many electrons here that it is as if you have inverted the type of doping that you had at the surface. So you first accumulate all the charge at the surface, all those electrons, bring them to the surface right below the gate, and then at some point you will have an inversion of the doping type. It's not a real inversion. You still have all the dopants in there, but you have so many charge carriers that it behaves as a very thin layer of an N region. And then what happens next? Now, from here to here, from the source end to the drain end, so far you didn't have any contact. So far you had two reverse bias diodes, but all of a sudden now there is a very thin N region that connects these two regions to N plus and, at the source and N plus at the drain regions to each other. It's a very thin region. It's, you still have to push resistors through it, carriers through it. It behaves as a resistor. Now you have, instead of having two diodes back to back, the diodes are still there. The diodes are still there, sorry about that. But now at the very top of that surface, you have an N region, so you go from N plus to N back to N plus. It's the same type of doping. So it's just a resistor at the very top of this, but the rest of the structure remains as before. Now that you have a resistor, you start to register a current here. Now there is going to be some current that can flow from drain to source through that external VDS supply. Now, an interesting thing about this resistor here, I call it RDS, is that I think that you should be able to see it by now, that I can control the value of that resistor with the gate voltage. If I put a larger gate voltage on that gate, between gate and source, a larger VGS, I make that layer that is inverted at the top thicker, or I will have more conductors at the surface, charge carriers at the surface, that will reduce that resistance for me. So I expect an inverse relationship between the voltage that I put on the gate and that resistance. And at the same time, I noticed that I need to provide just enough VGS for that inversion to happen. Before that top layer is inverted, nothing happens. So that voltage where I invert this doping at the top layer from P to N, I call it the threshold voltage. So my VGS has to be larger than the threshold voltage for all those interesting things to happen. Before that, I have two back-to-back diodes that are separated from each other by a P region, nothing happens. But as VGS goes above VTH, then we have that resistor. And now another thing that I can see is that that RDS value should be proportional. Well, whatever VGS that is doing the actual work for me, changing that thickness of the inversion layer or the number of carriers here. So that the effective portion is VGS minus VTH. Up to VTH, nothing happens. All those interesting things happens after you have that resistor created there. So I expect that to be proportional to VGS minus VTH, 1 over VGS minus VTH. And if you do a proper analysis and you go and look at how much charge I have accumulated in that region and all that, you can show that you can actually find the current between the drain and source terminal, I call it ID, from this relationship. Or you can, if you're interested in the value of the resistor is given by this value. Okay, so the VGS minus VTH part I hope is clear, why we have that VGS minus VTH part. But what are those mu n, C oxide, WL, what are those parameters here? Well, L is the length of this channel. Now, we have this narrow region from drain to source, extending from drain to source, where you have the current. I call that a channel. So L is the length of that channel. So this dimension is L. Or maybe, let me make it a little bit more. This is L, right? The length of the channel. So you expect that resistance to be inversely proportional to L, right? Sorry, directly proportional to L. The longer the channel is, the more is the resistance, right? The farther is the distance that the charge carriers have to travel. What is W? W is the width of this region. So when you look at it from the top, W is this width. And again, you expect the resistance to be inversely proportional to the width. If you make the device wider, it's as if you're putting more and more of these devices in parallel, like more resistors in parallel. So the effective resistance should go down. So that makes sense. So this is the W and L part. C oxide is the unit capacitance for that metal oxide semiconductor that we mentioned, right? And that tells you how efficient your device is in converting the voltage that you apply there to accumulation of charge. So what does that mean? You have a capacitor. In a capacitor, from basic physics, we know that Q is equal to the stored charge on a capacitor. Q is CV, where C is epsilon, the permittivity of the material, epsilon naught, permittivity of free space, area of the capacitor, and then the gap between the electrodes of the capacitor. So for a given value of a voltage, depending on what C is and how you make your capacitor, you can have different amounts of charge stored on that capacitor. What sets it? Well, a couple of important parameters. So epsilon naught is a property of the material, so we don't touch that. C oxide that we use here is unit capacitance. It is normalized by area, so area is not important here. Epsilon naught is not important here. So there are two parameters that you can play with. The thickness of that layer, G, the distance between the electrodes, or the type of the material, which sets epsilon R. And there has been a lot of research in microelectronic industry in order to optimize those two parameters. You want to use materials that have a really high dielectric constant so that you can store more charge on this capacitor. You also want to make that layer as thin as you can before you increase your yield problems, so that again the same thing happens. So C oxide here is a measure of how efficient that structure is in bringing in these, let's say, electrons in this case to the surface and storing them at that location. And then mu n is mobility of the electron. How fast does the electron move from one part of the substrate to the other? In this case, if you have injected an electron, let's say at the source end, how far does it take? How fast will it go from one end of the device to the other end? And then combination of these parameters give you RDS. So I'm not getting into the physics of the device here. You can go and study the book for a brief discussion on the physics, but I'd like you guys to have a feeling of what these parameters are and how they manifest themselves in terms of device structure and properties. So now we have a variable resistor, a great device. It's a device, it's a resistor whose value is under your control. You can use it in all sorts of applications. So if you notice, a lot of the electronic devices nowadays, instead of having a real knob, a real potentiometer to change a value, it's a virtual knob. You move a bar up and down by hand, and then how does that work? If it is changing an analog circuit somewhere, chances are that they're changing a resistor using an electrical voltage. So as soon as you have a voltage that is larger than the threshold voltage of this device, you have that resistor, you can play with its value. And that's live, that's in a circuit, but initially you set the range of values for this RDS by designing the proper dimensions for the device. So I have a variable resistor. So it's a resistor between drain and source whose value I can control with the gate voltage. Great device, but it's not what I wanted, or not yet. What I wanted in the past, and we saw it in the previous lecture, was that I want a nonlinear device. And the first thing that came to my mind was a controlled current source. Not necessarily a nonlinear device, but I wanted a controlled current source. I saw that I can do a lot of good things with a controlled current source. So a resistor is fine, but it's not that controlled current source. A resistor at the end of the story is still a passive device. It cannot really help me amplify a signal. A passive device only dissipates energy. It doesn't help you convert energy from one domain to the other, right? It's a linear device. I want a nonlinear device. I want a nonlinear device where I take the energy from my battery, my power supply, and add it to the signal that is at a very high frequency or a different frequency. So, interesting device, but still not what I wanted to do. What do? I keep, now that I have the channel between the source and drain. Let me play with the VDS value now. Just add a little bit of VDS. I started with 10 millivolts, which was just too small to do anything important or anything meaningful. Let's just increase VDS and see what I can do there. Let me draw that structure again here. So I have my N region here, N region here, and this is the P-type substrate, and then I have the dielectric, and on top of that dielectric I have my gate contact, right? So the gate is physically isolated from the channel. And I'm going to take source as the ground. And remember, the choice of ground is arbitrary. You choose a node in your circuit as your ground potential and measure everything with respect to that. So I'm going to choose the source to be ground, make my life easier a bit, and then apply 2 voltage sources between the drain and source and gate and source. And I'm monitoring these 2 currents. So there's the ID and there's IG. So what is IG? I'd like you to maybe pause the video for a second and tell me what you think IG at DC is. If you answered 0, you're correct. Why is IG 0? Well, because it's a capacitor. A DC current cannot go through the capacitor. You charge it up and that's it. Everything stops. So IG will be 0. This is actually a very interesting property of these MOSFETs that we will see, and it makes our lives in terms of analyzing circuits with MOSFETs much easier. Gate is insulated from the rest of the structure. It actually even shows up in the device symbol, as I will show you in a second. But ID, we already saw, can be variable, right? We already had a variable resistor. Now, what I do is that I keep VGS to be larger than VTH. So I establish the channel between the drain and source. But then I start to add a little bit to the drain voltage, slowly over time. And then what happens is that the channel that initially you had from here to here looking like this, it's going to deform. At the drain end, you have less voltage difference between the gate voltage and drain voltage. That voltage is smaller. If you look at VGD, initially, for small values of D, drain voltage, VGD is larger than VTH, but VGD is less than VGS. Why? Because I'm adding a little bit of voltage to the drain end, right? So VGD is VG minus VD, and VGS is VG minus VS. VS is 0 in this circuit that we have. So if I add a little bit of voltage to the drain end, VGD will be less than VGS. And then what does that mean? Well, the channel at the drain end started to become narrow compared to the source end. So my resistor will look like the shape of the channel will go from something rectangular to something more like a trapezoid, right? So I have a deeper channel at the source end than the drain end. So I expect this resistor to start showing some undesired, well, not undesired, but nonlinear behavior. And that, in fact, is what will happen. So in a situation like this, if you increase VDS beyond a few, maybe tens of millivolts or hundreds of millivolts, your relationship for drain and current becomes like this. So AD is going to be 1/2. So far this is what we had before, right? 2 VGS minus VTH inside the brackets cancels the 1/2 in front of it. This is the relationship that we had before, but because of this change in the geometry of the resistor, once you do the calculations, you'll see a new term here. So initially it was VDS times this. Now you have a nonlinear term. added to the equation. What does that mean? It means that as you initially keep ID and VDS, if you look at ID VDS curve, initially everything was nice and easy, right? Everything like in linear resistor, everything perfectly, you know, like the old days. Linear device operating with a small voltage and current, right? But as you keep increasing VDS, at some point this nonlinear term, this VDS squared that you see in the equation, comes into play and starts to bend this curve downwards. Right? It's going to show some nonlinearity. It's going to behave like a nonlinear resistor. Now, if VDS is large or VDS is small, you get two different values of current that are not necessarily, well, they're not linearly proportional to each other anymore, right? And that's still okay. I can live with a nonlinear resistor. You know, I still need a controlled device, and this is good enough for a lot of applications. But if I keep increasing VGD, if I keep increasing VDS, at some point, this condition that I have here is not going to be valid anymore. Right? So at some point, VGD can drop below the threshold voltage, right? If I keep increasing the drain voltage and keep the gate voltage constant, let's say the threshold voltage is 2 volts, my gate voltage is 3 volts, I can keep increasing VDS, and at some point, let's say I go past the 2 volts that I need to make to keep the channel at the drain end. So what will happen at that point is that your channel, when your VGD becomes smaller than VTH, your channel vanishes at the drain end. So you will deal with a situation where the channel now extends from here, the source, all the way to very close to the drain, just about where it needs to meet the drain, the channel vanishes. You don't have the condition to keep the channel at that end of the resistor anymore. And this is called channel pinch-off. And something super interesting happened at this point. When the channel pinches off, when the channel vanishes, the dependence of ID to VDS vanishes as well. We are going back to what we had, similar to a situation in the BJT, that you had a reverse bias diode that just took all the current that came to it and put it on the other side. Either, you know, whether it liked it or not, similar thing is happening here. Your source and all the way to the very near of the drain end, you have a channel, you have a resistor, you bring all the carriers all the way to the edge of the drain, and then at the drain corner, the channel has vanished. That channel has pinched off. But all those carriers that have got themselves to that corner are so close that they just jump over and then they appear in the drain terminal. Well, similar thing happened for BJTs, and now we have a current source, right? So if the voltage drain, across the drain, VDS, if you go beyond that and if it is not affecting the current anymore, well, that's a current source. Well, I'm getting what I was hoping for. So what is the value of that current source once the channel pinches off? So this is still a resistive region, but at some point when VGS is larger than VTH, so I have my channel at the source end. But VGD is less than VTH, so the channel has disappeared at the drain end. I can go and see what happens to ID. So when does the pinch-off happen? When VGS is equal to, VDS is equal to VGS minus VTH, just at that threshold point. So if I go and put that value of VGS minus VTH here for the VDS, that's the threshold. You know, after that point, the current didn't change, so it just stayed constant, right? This is, let's say, VGS minus VTH. This is your, you know, you just go past the threshold voltage or drop below the threshold voltage. After that, the current doesn't change. So if I take the value of the VDS at that point and use it in this equation, I can figure out what the current is going to be from that point onward. From that point onward, it doesn't depend on VDS. And I can show from that equation that it's going to be mu n C oxide W over L times VGS minus VTH squared. So in here I had a nonlinear resistor between the drain and source, right? In the beginning I had the linear resistor, right? So this was a linear resistor for very small VDS values between drain and source, right? And now I have a current source whose value is given by this. Notice that it doesn't depend on VDS. So I have a current source. Drain and source, right? Same device. I played with the gate source voltage and drain source voltage a bit. Same structure. I'm getting three different functions out of it. I have a linear resistor for small VDS values and large enough VGS. I have a nonlinear resistor if I push my VDS to slightly larger values. And I can actually get a current source out of it if I make the channel pinch off at the drain end. I can actually use the same device as a capacitor too with removal of one of the extending one of those doping regions, but we're not doing that. But anyway, same structure gives you these three different functions. Very, very interesting, very, very useful, especially this one. For an analog circuit designer, this is really interesting. I have a current source. I have that device that I was looking for. Not only it's a current source, it's a controlled current source. I change the gate source voltage, and as long as I keep it above the threshold voltage and make sure that the gate drain voltage doesn't fall below the threshold voltage, I will have a current source. Now, you can see that there is a little bit of difference, well, major differences between this and a BJT. In a BJT, the only parameters you had for the device was just IS, which is a property of a function of the size of the device, and maybe n ideality factor, but for most BJTs that was close to 1. And that was it. It was IS e to the VB over VT. You normally don't change temperature if you want to control these devices, right? So you really didn't have that much of an option. You can make the device larger or smaller if you're making an IC, but there's really not much that you can do beyond that. And in here for a MOSFET, that tool is the change in W and L ratio. If you make the device wider, it's like you put multiple of these in parallel, and therefore you get multiple amounts, W times the current out of this thing. And if you make the channel longer, well, it just becomes more difficult for a charge carrier, electron or hole, to travel from one end of that channel to the other end. So you expect an inverse relationship between L and current. And then mu and C oxide was how efficient is your MOS structure in converting voltages into charges and mobilizing them. Now, so this is a MOSFET, and you can imagine that the P MOSFET looks like this, but instead of having N doping for the drain and source and a P substrate, I switch all the polarities. I will start with an N substrate and create two P regions for the drain and source, and I get my complementary structure as a P-type MOSFET. The N MOSFET means the channel is N-type. N-type MOSFET, N-channel MOSFET. P-type means that the channel is P-type. Now, so very interesting device, okay? What is the symbol? The symbol for a MOSFET is this. So you have your gate, and we actually show it on the symbol that the gate is isolated from the rest of the structure by a gap. So this is your gate, drain, and source. Now, if you go back and look at the structure of a MOSFET and look at it for a second or two, you realize that we actually have another terminal. So this is your, let me maybe mark it with red here. So this is one terminal, this is one terminal, this is one terminal. So that's the three terminals that I showed you on that symbol. But there is another terminal. There is another node here in this circuit that has to be connected to a voltage, and that's this substrate, right? You cannot have a floating substrate. So a MOSFET in reality is a 4-terminal device. You have a body terminal, which is the substrate, and then the 3 terminals that we've been talking about so far. If you're designing an integrated circuit, you have to specify where that body is connected to. You actually have to connect that terminal to a voltage yourself. In most technologies, you have that option. If you're using a discrete circuit, discrete MOSFET, what they normally do is that they short circuit the body terminal to the source terminal internally. So inside the device, inside the package, they short circuit the body and source terminals to each other. So although this looks like a symmetric structure, and in fact it is, right? So if you have an integrated MOSFET, the drain and source are interchangeable. You can use one terminal, one end of the device as drain, the other end as source. There's no difference. Unlike a BJT, where you usually have much higher doping at the emitter end than the collector end. For a MOSFET, it doesn't matter. You can switch, right? But for a discrete MOSFET, because of that connection, that internal connection where they go and connect the source to the body, it's not symmetric anymore. All of a sudden, the source behaves differently from the drain terminal, which you didn't expect from the structure, but it's because of the connection. Sometimes you see that connection explicitly on a symbol. So this is the body terminal, and you have to connect it somewhere. But for discrete devices, as I mentioned, we have these two short-circuited to each other. And for that reason, in most drawings of MOSFETs, you actually don't even show that body terminal. Although it is there, but because you don't have access to it in discrete circuits, you don't even have to show it, right? It's already connected internally to the source. Now, so this is my device. Then the directions of currents. This is what I choose for D and S, and this is IG. But if you go back to the answer you gave a second ago, IG is 0 because it goes to a capacitor electrode. And IG is 0 at DC or AC. ID, then KCL forces it to be equal to IS, right? So, life seems easier with MOSFETs than BJTs. With BJTs, the emitter current was the sum of the base and collector currents. In this case, because IG is 0, ID and IS will be the same. And then I have a couple of equations for ID depending on the operating region of the transistor. So I can go and look at a couple of different situations. I can have a situation where VGS is larger than VTH. Or let me just name them. So operating regions. So operating regions for MOSFETs, right? So let's start with the case that I had a resistor. I call that triode, right? In triode region, I had a gate source voltage that was larger than VTH and a gate drain voltage that was larger than VTH as well. Why did I need to do that? In order to have a channel at the source end as well as the drain end. And if that is the case, then I could see that my current voltage relationship is given by this expression, 1/2 mu n C oxide W over L. Two here as well. Okay? So in this case, I have a resistor. And then we saw that if VDS is small, we said tens of millivolts or so, then you can ignore this nonlinear term at the end of this equation. So this nonlinear term can go away. and you have a resistor that is more or less responding linearly to VDS. But if you increase VDS, it becomes a nonlinear resistor as long as these two conditions for VGS and VDS are satisfied. Then we increased the drain voltage, and we had a situation where VGS was still larger than VTH, but VGD, because we keep increasing the drain voltage, became less than VTH. Okay, I can write this in an equivalent way, right? Or so VGD, I remember that is VG minus VD, or I can write it as VGS minus VDS. Okay, so VG minus VDS minus VD minus VS. Okay, so I add and subtract the VS to that, and this becomes the same as saying VDS. Okay, if I put this equation, if I put this in here, VDS is larger than VGS minus VTH. Same thing, right? It's as if we, when we say VGD is less than VTH, we don't have a channel at the drain end. What it turns out in terms of VDS is that VDS is larger than VGS and minus VTH. We use this second equation, this equation here, in circuit analysis more than the first one, and the reason for that is that we'll see that the drain end is sometimes, or most of the time, is your output, and you know the voltage at that output node. You want to see if the transistor is in the proper region of operation by looking at the output voltage instead of the gate and drain voltages. Now, so going back, these two are equivalent, VGD less than VTH or VDS larger than VTH, VGS minus VTH. Let me move the whole thing a bit to the left. Oops. And if this happens, I have a resistor between, I have a current source at the drain end, and we saw that ID is 1/2 mu NC ox W over L VGS minus VTH. The current through the drain does not depend on the VDS voltage anymore, right? This is what I need from a current source. Great. And then we didn't talk about it, but obviously the first operating region of where we started was when VGS was less than VTH. We didn't explicitly talk about it, and VGD was less than VTH, right? If both of the voltages at the drain and source ends are less than the threshold voltage you need to establish a current, to establish a channel, obviously the device stays off, two back-to-back diodes, and ID remains 0, and then we know IS is also 0. And this is your cutoff region. Okay? So these are the three possible operating regions for the transistor. Again, you can come up with another one and say, what is VGD larger than the threshold voltage and VGS is less than the threshold voltage? Well, it is as if you put a MOSFET and connect the drain and source terminals to the opposite polarities. And we said, a generic MOSFET is symmetric, so that's really nothing other than the active mode that you have here. Just rename the terminals, and you get your active mode back. And as we said, we love the current source that we get here, but in analog electronics, we also appreciate that variable resistor a lot as well, right? So we use that variable resistor in analog circuits a lot. If you want to change the gain of an amplifier automatically by changing a resistor value, instead of somebody going there and manually changing it, you can use a variable resistor. And then in cutoff region, again, it's a nice other tool in our analog toolbox as well. I want to disconnect two parts of the circuit from each other, so I can put a MOSFET in between and control whether I have an open circuit between those two nodes or a short circuit. Short circuit meaning that I put it from cutoff, take it from cutoff, put it in triode region with a very large VGS minus VTH value. so that it becomes like a small resistor. A very, very useful device, very interesting device. One more point I just wanted to make. Oh, now there is an unfortunate naming convention here, where the active region of MOSFETs is called saturation in most textbooks and literature in the field. Why do I say it is unfortunate? Well, because in BJTs that we learned first about, saturation was normally an undesired operating region. We didn't want the transistor to enter saturation. In MOSFETs, if you use that terminology, you want the transistor to be in saturation region if you want a current source. And that can be a bit confusing. So to avoid that confusion, I'm going to call it active region. But when you refer to your book or other references and you see that they say the transistor is in saturation, it means active region for MOSFETs. It's not the same thing as BJTs. Now, you may have a question here that, we have this device that can actually be made smaller than a BJT. It's, nowadays it is cheaper to make than a BJT, and it can serve so many purposes. Why do I need a BJT? Why do we still keep those things around? If this MOSFET can do all those fantastic things and beyond. Well, the answer is that, MOSFET is a great device, but it falls short when compared to BJTs in terms of how efficient it is as a nonlinear device, especially in amplifier circuits and so on. And the reason for that is that the nonlinearity you have between the input and output in a MOSFET, the ID is the output, VGS is your input. This nonlinearity here is quadratic for a MOSFET. For a BJT, if you look at the nonlinearity between IC and VBE, it's exponential. IC is I as e to the VBE over VT. And that exponential relationship, that's, there's nothing faster than that. No growth is faster than exponential. And that super fast increase in current means that you're super sensitive to changes in VBE, especially when compared to a quadratic relationship like this. And what that translates into is that you get more gain out of a BJT than a MOSFET for, similar conditions and situations. And nonetheless, MOSFETs are the dominant devices nowadays. It's, you make them, or you use them in billions. In your pockets, you have cell phones that nowadays have gigabytes of RAM. And each bit in that RAM module is made of at least one transistor and one MOS capacitor. So when you have 1 gigabyte of RAM, that's 8 billion MOSFETs just for the RAM cells. Forget about all the control circuitry and things like that. And we're not talking about processors or GPUs and other things. On the displays, a lot of the display transistors are actually field effect transistors. You switch a transistor on and off to a pixel on and off using a MOSFET switch, right? And you can use a matrix, so you don't really need one MOSFET per pixel, but there are different technologies. But as I said, you still have discrete circuits, and you usually design with discrete elements, and that's where BJTs are dominant. You need to learn about MOSFETs for power electronic applications and a lot of other cases. So the next lecture is going to be about how to solve circuits that have MOSFETs in them.